Hello everyone. Discuss contest 20. Pretty hard contest, especially the last problem probably was a little bit too hard, but it's not that hard actually. Overall nice contest and the results are pretty nice, so let's discuss. So start from problem 1. Problem 1 is today is very straightforward. So again, I pick random problems. Sometimes the first problem requires some thinking. Today it's actually not. So you just need to do what's written in the problem statement. But again, it requires some programming. It's you need to work with strings as integer numbers. So the input is given you as a string, but it actually represents an integer, and you need to be able to calculate sum of digits of this number. It's not as difficult actually. Let me speed up a little. Okay. Let's do it twice faster. So I code really fast here. Again, my first approach is kind of C. So I don't like in C. I don't know how to do it nice in C++, because you need to transform your number to string. The only thing I noticed is you can actually from after the first time you calculate sum of digits, you have a small number. So sum of the digits of this number is up to like 100,000. So it's like up to a million. So you can calculate this sum of digits and then store it in integers instead of string. But then I said, so you need to have separate code for calculating first sum of digits and then have different code to calculate sum of digits of integer. So because first you have string, you need to calculate sum of digits, and then you have integer, you need to calculate sum of digits. So instead, I rewrite it like this. So I just convert my integer to string. So I always have a string, and every time I calculate sum of digits as integer, and then convert this integer back to string. So every time I have string. Yeah. So this is the whole code on the left. So let's see. So they have this string, just input string. So I will always store my current number as a string. And here I will just see if I have more than 2 digits, more than 1 digit, I will calculate sum of digits here, put it in this integer, and then transform it back to a string. So in the next iteration, again, I have string, I can do all the same. So that's maybe, okay, this is the easiest approach I can find. Probably it was easier to implement it in Python actually. So in Python you don't have problems with big integers, so you can just store everything in integer and transform it back and forth, or you can just store everything to strings and then transform its integer to string. Up to you. So maybe it was easy to write in Python. I'm not sure, but this is C++ code. It's actually not as complicated as well. So that's problem A. So quite easy. Just do what's required in the problem statement. The only problem is that to deal with integers and strings at the same time. Okay, it's not very hard thing to do. Just need some careful implementation. Okay, this is problem A. Let's go to problem B. Problem B is actually pretty classical problem. You need to find a subsequence in a given sequence. And in this case, you have string, and you need to find a subsequence of letters which forms this string hello. And again, if you never saw this problem before, you can do it using greedy approach. So it works not only for this problem, it can work for any problem when you need to find a subsequence. So if you have a sequence, basically array, yes, and you need to find some specific subsequence, you can do it greedily. You just go from left to right, pick the first character, then pick the second character, then pick the third character. Every time you find the leftmost character from your current position. And I do it like this. So I store this string hello in a separate string here for simplicity. Here I just iterate all characters of my string and check if I see the next character of my string t, so of this string's hello. I just increase this counter. Yeah, see. So first I will be looking for character 0, so it's H. Then when I find character H, I will be looking for character E, then for character L, then again for character L, and so on. So every time I remember which character I'm looking for. And if I see this character, I just shift this pointer one position to the right. And I add this dot in the end, so I don't have special case when I'm out of characters. So I will never find this dot. So if I find all the characters of string hello, my pointer will stop at this position. Yeah. So I check if my pointer stop in position 5, then I found the string hello. Yeah. If not, it means I don't have subsequence hello in my sequence. That's it. So pretty classical problem. If it's the first time you see it, it's good. So you've learned something new today. Let's go to problem C. What's problem C? Okay. I guess today's day of greedy algorithms. We have a lot of problems solved using greedy algorithms. Problem C is one of them. So what we need to do in problem C, we have a string. We need to remove some number of characters in such a way that the resulting string has small number of different characters. Yeah. And again, it's easy to see that if you want to remove some characters, you need to remove characters which occurs less number of times. Yeah. So if I have some number of characters A, some number of characters B, and I want to decrease total number of distinct characters, you need to remove either all characters A or all characters B. Yeah. And it's easy to see that a greedy approach works. So you want to remove the character which occurs less number of times. Yeah. So what I'm doing here, I'm counting how many characters of each type do I have here. Yeah. Then I will sort all the characters by the frequency. So starting from the least frequent to the most frequent. And in this order, I will start to remove them. Here I forgot to sort. I will find it later. So basically what I'm doing here, I make array of pairs, number of characters and the character. And then I will need to sort it. Okay. What? Also you need to output the number of characters in the end. Okay, that's easy. Yeah, here I find that I didn't sort. I remove character A, you see, which when I need to remove actually character B and C, because I forgot to sort them here. That's basically the whole idea. So again, we iterate over all characters here. Let me stop. So we iterate over all characters in the order of frequency, starting from less frequent to most frequent. Yeah, I do it by sorting these pairs here. See, there are multiple ways to do it. It's just easier for me to do it like this. So I make array of pairs and then sort it as array of pairs. Yeah. Then in this order, I go from left to right. So I pick the character, see if I can remove all characters of this type. So if this number of occurrences here is less or equal to k, then I remove all these characters. I basically mark them as removed here. And decrease number of characters I can remove. So k is number of characters I can remove. Yeah. So if I can remove all of them, I remove them and decrease k by this amount. Yeah. If not, I just leave this character as this. So RC is number of characters that I left. Yeah. Then I output RC and then output all the characters not removed. Here, see. So I iterate for all character. If it is not removed, then I print it. Pretty straightforward problem. Again, the only intellectual part is this greedy algorithm. But in this problem, I think greedy approach is kind of intuitively correct. So again, you need to pick some characters. Again, you need to transform your problem from removing some characters in such a way that the number of distinct characters is minimal to the problem when you need to remove all equal characters such that total number of characters is imposed k. Okay? That kind of makes sense. If you remove characters but not all of them, you keep the number of distinct characters the same. Yeah. To decrease number of distinct characters, you need to remove entirely some characters, all occurrences of the same character. Yeah. And we do it like this. We remove all the characters in order of number of the occurrences. Yeah. So that's it. That's problem C. Again, some greedy algorithm solve this problem. Problem D. Oh, problem D is fun. Problem D is fun because last week we had actually similar problem, but with smaller constraints. So what we need to do in problem D, we have some array A, and we can increase some values, and we need to increase them in such a way that all numbers in the array are different. Okay? So we need to create array B with the same characters. We need to create array B. So all elements of array B are greater or equal in array A, and they are all different. And last week we discussed that you can do it using greedy algorithm. Basically, you pick the element, and if you have equal elements, you increase one of them. Yeah, so you take the element and increase it until it's unique. You can do it like this here because number of characters is too much. So you have n up to 300,000, and this approach will work in n square. So instead, I do another approach which works in n log n because of this sorting. So what I'm doing here, let me show you actually. Okay. So what you can do, so you have some number of characters, so some number of integers. So you have like here 1, 1, let's say 2, 2, 4, 10, 11, something like this. So you go from left, so you sort them, yeah, and go from left to right. And you basically, idea is to keep the array sorted. So you want to keep the array sorted, but make all the elements different. Yeah. So I go from left to right and just pick the minimal value, which makes array sorted, but also keep all elements distinct. Yeah. So I go from left to right. Left element I can just left it as it is. So next element is the same. So I need to increase it. So I cannot keep equal elements. So I increase it to 2. Yeah. Next element is 2. And again, I have 2 equal elements. So I need to increase it in 3. Yeah. Next element is also 2. But again, I want to keep my array sorted. Yeah. So this element should be at least 4. So I move it to 4. And again, this should be at least 5. So this element is already greater. So I can keep it as it is. And so on. So I go from left to right. If my element is, so again, if my element, like here, okay, if it is less or equal than the previously put element, then x. So I make it equal to x plus 1. Yeah. So that's the whole idea. So to do this, I need to sort my array. Let's stop here. So I need to sort my array first. Again, I do it in the same way as in the previous problem. I make an array of pairs because I need to keep indices. Yes, I need to keep in which order these were in initial file, in initial array. So I make this array of pairs, sorted. Yeah. Now I know all the elements in the sorted order. So I go from left to right. Remember the last element. If my element is less or equal to the last element, I make it equal to last element plus 1. That's it. So so this approach works in n log n time because of this sorting. So everything besides the sorting actually works in linear time. So that's how you do it. Again, again, problem like this is very classical. So today's day of classical greedy algorithms. So that's how you normally do it. So you sort the array and just keep it in sorted order and just increase value to keep it sorted and also make all elements distinct. The same way you will solve this problem if you can only decrease numbers. If you can only decrease number, you go from highest element to lowest element, in the same order but in reverse order, from largest elements to smallest element. Yeah, and just do the same. So that's it. That's problem D. Okay, I discuss first few problems very fast because they are kind of easy. We will move to hard problems, then we'll spend some time discussing hard problems. Especially two last problems today are pretty hard. So let's go to problem E. Okay, problem E is actually nice. So we have, again, it's greedy algorithm, but different. Okay, it's kind of similar to all previous ones. What we need to in problem E, we need to have, we have array. We can increase some elements of this array. We have upper limit, so we cannot increase elements up to number r. Yeah. And we need to make the average of all elements at least this value. Yeah. So we're given the average value of the values. And the trick I'm using is moving from average to sum. It's quite popular trick. Again, let me show you. It's quite easy. Okay. So what is the average value? Average value is just sum of all elements. Sum of all elements divided by number of elements. Yeah. And I want this value, so I want this to be at least average. Yeah. So my average calculate like this. I will move this n to the left. Yeah. So now I just have an equation that sum of all elements should be greater or equal than n multiplied by average. Not average. Quite popular trick used in many problems when you're given some average. So the first thing you kind of want to do is multiply this average by n. So now you have an equation on the sum of elements, not average. It's just easy to work with sum of elements when average. Yeah. And now the problem is like this. I can increase some numbers, and I want a sum of these numbers be at least this value. Yeah. And I have a cost of increasing elements. So this bi is cost of increasing one element by one. And again, it's easy to see that you can increase this sum by one, paying this amount of, okay, writing as many as okay. So you're paying this amount of money by increasing one element by one. It kind of makes sense to increase elements with lower cost first, because there is no difference which element you increase. It kind of makes sense to increase elements which are more cheap. Yeah. So what I will do here, again, I will sort all elements by this value b. Where I'm sorting. Okay, here I first check if my sum is already good. I'm just writing 0. If not, I'm doing all the same things. So it's again, code is actually the same as before. I make array of pairs and sort it. So now I know elements in order of cost. And here I will go from, okay, I'll do something strange. Okay, here I decided to do it like this. So here I iterate, here I iterate over all these pairs, and I take only value I. I'm interested in value I. So basically, I iterate over all elements in order of increase of this value b. See? So I sorted array of pairs and then take the second element of this pair. Okay, so I'm going from cheapest elements to most expensive elements, and every time I look at the element and see how much I can increase this value. I can increase it by minimum of these two values, see? So I cannot increase it more than r, and I can increase it more than current difference of sums. Yep. Okay, sure. Yep. So this, so I can't increase it to more than r, so this is limit of how much I can increase this count. And I also don't want to increase it more than s. So this s is my current sum. S is the sum is a desired sum here. It's just here, see, and multiplied by average. Yeah. So D is the maximal amount I can increase this element. Yeah? So I find this amount increased by this man. So this cost will be added to my result, and this amount will be added to the sum. And then I move to the next element and try increase it, and so on. And in the end, I get the minimal possible cost to increase all elements. Again, today we have day of greedy algorithms, but they all are kind of natural. So sometimes greedy algorithms are not that very natural. So you think like maybe it can be solved with greedy algorithms, but it's not that obvious. Here it's kind of more obvious. So here you can if you need to buy this number of identical balls, but they have different costs, you start with the cheapest balls and then in this order buy them and so on. Okay, let's go to problem F. Oh, problem F is interesting. Problem F is like this. Okay, let me write something first so you get my idea. So we need to construct number out of two sequences of 9 digits. So first player picks some 9 digits here. So so I put some 9 digits here. Such that this number is not greater than a. So it's from 0 to a. Then the second player picks some digits. So let's say y. And so this number is not greater than p. Yeah. And the question is it okay? So the second player wins if this whole number is divisible by m. So let's say modular mod, okay, divisible by mod equals 0. So the question is, who will win if both players plays optimally? Okay, several things to notice first when you read this problem statement like this. First of all, you think, okay, this problem is about modulars, so about remainders of some modular. So I given this modular, so now all my arithmetics only works with this modular. So I think about all the numbers modular this mod. So if I have this model, I think only about remainders by this model. Second thing you notice is this model is actually small. So this model is up to 10 power 7. 10 power 7 get like 10 millions. 10 millions is small number, yeah? So I can just check all possible remainders modular mode, yeah? So this give you again, this give you some insight of what the algorithm may look like, yeah? So if some number is small, you think, okay, I can iterate over some values. Again, at least over some values up to this modular. Again, now you think, okay, now you have this, okay, you have these observations. You start thinking about algorithm. Again, what you can think, okay, you are the first player. So you pick some digits here, yeah? So the only difference you make is the remainder of this number modular mod, yeah? Again, we're looking at all numbers only at the modular this mode. Yeah. So which remainders modular mode you can produce? Do some remainders modular. So if you put some numbers here, can you put some number a in the left part? Okay, not a, plus a number x in the left part. Yeah. The remainder of this, okay, and this number y. Yeah. So we have 9 digits number x, 9 digit number y. The total number will be equal to, again, 10 power 9 multiplied by x plus y. Yeah. And modular arithmetics works like this. So if you have some modular something, let's say modular m, let's rename it to m. So I can modular mod, it's strange. Yeah. So this modular m, you can calculate it by looking at both numbers modular m. Yeah. So it's the same as taking this 10 power 9x modular m plus this y modular m, yeah, and everything modular m. Now, if you look at this left number here, again, you multiply something by something modular m. It is the same as multiplied in 10 power 9 modular m multiplied by x modular m. Yeah. So you can take all the numbers modular m when you work in modular arithmetics. And now, again, the key observation is that this number x will produce some modular. This modular only depends on this remainder modular m. So, and this modular m is number from 0 to m minus 1. And like we noticed before, this model is small. So we can track all these numbers. So we can track all possible numbers we can put as the first player and check if the second player can win. How to check if the second player can win? It's actually easy. If you know, again, if you know this value, you know modular, then you can calculate which number y will give you 0. So I need this to be 0, modular m. Yeah, you see. So this only unique number y, okay, not unique modular m, but again, the smallest number y is just m minus your number, basically. That's it. So I will iterate all number x, calculate this left part, then calculate the right part, which give me a remainder 0 in the end, and check if this number y is less or equal than b, then the second player can put this number and win. I will check if there is at least one number x which will not allow second player to win, then the first player will win. Yeah. So let's see. Yeah. So here I noticed that model is small, so I can again. So that's first thing you do. You read the problem statement and find some interesting details in the problem statement, and very often they hiding these interesting details in the constraint part. So you look in the constraint part and kind of think, okay, what can I do with these constraints? Can I iterate over something? Can I brute force something? Something like this. Yeah. I can't hear reading from the, yeah. So what I will do, I will iterate over all numbers that first player can put. First player can put numbers up to A, and I'm only interested in numbers up to modular. Here we need to put A plus 1. I will fix it later. Yeah, so I can put number A, so X should be less or equal than A, and also X cannot be greater than mod, because I'm not interested in numbers greater than modular. Yeah. Oh, yeah, I'm doing it like this. Okay. Basically, calculate X multiplied by 10 power 9. I can just do it like this. Why not? Here I calculate number Y, which gives me 0 as in the result, and check if this number is greater than B. Then the second player cannot pick this number, so the first player will win. Yeah. So I just output 1 and return. If the second player can't win, then I output 2 in the end. So if all the numbers, for all the numbers, second player will win. You also need to, okay, you also need to print the digits that first player will give. I do it like this. I convert X to string and then add zeros in it. I believe in C++ there is a function which does exactly this, but I don't know. So I just do it like this. I convert it to string and then add these zeros to the left. It's not very efficient. It's square time complexity, but it's just 9. Nobody cares. Okay, here I will have wrong answer. Quite surprising, actually. I just first thing I checked when I looked at, so I never put integer something, so I don't have integer overflows. I checked that I don't have integer flows, and then think what can go wrong, and then I noticed here that I have a number less than A, and it should be less or equal than A. So I fixed it like this. So that's it. That's problem F. Again, kind of mathematical problem, but the programming part is very easy. So this is the whole program. Good. That's it. Let's go to, now we have 2 problems left, actually quite hard problems. So let's go to problem G, problem H. Problem G. Problem G, you have a binary tree. So here, okay, it's kind of strange. Okay, so strange definition of binary tree here, but it's actually normal binary tree. So like you expect it to be. So it's normal binary tree when you enumerate vertices from top to bottom, left to right, like usual actually. Again, it is because it's unusual because you use number elements from 1. Normally you number one from 0. So, but that's it. So I just checked that it's actually what I think it is. And you have queries like this. You're given some vertex of this tree and some number h, and you look at all nodes with distance less than h, and the happiness for this node will be equal to this h minus length of the road. So, and you need to calculate the total happiness you have from all possible vertices. Okay, here I'm already writing what's going on. Yeah. So I'm thinking how my tree actually look like. So how all possible paths from my, so this, imagine you have this node in there. So let me show you better picture. So what's going on? So imagine you have some node. Let's have node X. So how do all the paths look from this node X? There are multiple ways to think about it actually. Here, because it is binary tree, I will just trace all parents of this, all ancestors. So because I have full binary tree, the number of ancestors of this node is up to log n. Yeah. So I can just iterate over all of them. Yeah. Now, how all the paths from node X looks like? I have paths inside my subtree here. Not much better. And then I have paths like this. I go up to some of the parents, to some of the ancestors. So I can go in red. So there are paths like this. I go from node X to some descendant here. Or I can go to some of the ancestors, then go to my brother here, not to brother this node, yeah, and go inside this is another subtree, and go inside this subtree. Now, what we need to calculate? We need to calculate. No, let's think about. So okay, I will write the formulas. Okay, let me write the formula here again. So I'm looking at the following thing. I look at the sum of numbers h minus length. Let's say x. This is y. Yeah, length y. Let's say ly like this. Okay. Okay. So let's so it's not confused with this l. Yeah. Okay. Let's call dist. Let's get dist of y. Yeah. And again, this is the sum I want to calculate. Yes, this is the happiness is h minus the length of the path. Yeah, so I will just rewrite this formula like this. I will take sum of h's. Sum of h's is just number of elements, like number multiplied by h. So h is the same in this sum. Yeah? So it's number of elements in this sum minus sum of these distances. So this is number of vertices I can reach. So it's number of vertices with distance less than h. Yeah, and this is the total distance. Let's look at the first part first. How to calculate number of vertices I can reach? Again, all my paths looks like this. I either go to my subtree or could go to one of my ancestors and then could go to one of the vertices here in the subtree. So what I need to do? I need to count number of vertices with distance less than h. How can I do it? Easiest way is just remember all the distances to the nodes in your subtree. You can do it because you have perfectly balanced binary tree. Yeah. So again, you have. Let me write the binary tree. Yeah. Okay. Let's say of size something like this. Okay. Good enough. So every node will contain array of all distances to all elements in this subtree. So here I have only one distance, here I have only one distance, here I have an array of 3 distances to all 3 nodes, and here I have an array of 3 distances, and here I have one, and here I have one, and so on. So here I will have array of all 7 possible distances, and here I will have array of all distances. How many I have? 7, 8, 9, 10, 11, 12, 13. Okay, something. Yeah. Yeah. So in every node, I will contain array of all distances to all nodes inside this subtree. We can do it because we have perfectly balanced tree. So total size of all these arrays will be n log n. Because every node belongs to log n subtrees. Okay, so we can store for every node array of the size equal to the size of this subtree. This will immediately allow me to find the number of elements. So I will sort all these arrays. And now when I'm looking for the number of elements with distance less than h, I will just do binary search and find the prefix with distance less than h. Okay, exactly less actually, less than h. Yeah. That's it. So that's how I will count number of elements with distance less than h. Okay. So I will split my problem into log n problems of finding elements inside the subtree. Yeah. Now, for example, here I need to find elements with distance less than h. Yeah. Then I go here, and then I go here, then I go here. So I know this distance. Let's say this distance is, I don't know, d. Yeah. So in this subtree, I need to find all elements with distance less than h minus d. again, it is the same problem, but with different constraint here. So in this subtree, I need to find all elements or all vertices with distance less than h minus d. I will do it using the same binary search. So I do binary search here, in this, then do it in this subtree, and all in every brother of my elements on my path. Yep, do it here. Every time I do it in log n time, I have log n subtree. So in log square time, I'm done. I believe it can be solved faster. I believe it can be solved in log n, but it's not required here. You can do it in log square. It's just fine. So that's basically my approach. Okay, here I'm writing formulas again, the same formulas. So how I do it? No, first I will construct my tree. Okay, I don't need to construct. It's perfectly balanced tree. You don't need to construct it explicitly. So I read the data. Okay, I enumerate everything from 0. Here, see. So my lengths start from 1 to n minus 1, and 0 is the root. Just more convenient for me. Now I take a node. Here you see I take the node, and now I will look at this node and all its ancestors. Okay. Yeah, do it like this. Here I just mark for myself the places when I need to calculate something. Now here I pre-calculate these arrays of all nodes in sorted order by the distance. To do this, I will. Okay, it's not very pleasant, right? So what I will do from bottom to top, and just maybe not, okay. It is very short way to do it. Maybe not very clear. Okay, let me finish writing it. Then I will explain you what's going on here. That's it. So here, what I'm doing, I go from bottom to top, and for each node, I maintain the array of all distances in sorted order. So how I do it? I go from bottom to top. Every time I take the node, I sort all elements of this array. So I have it in a sorted order, and then push them up to my parent. Yeah. So then I go to my parent. I have all elements from my left son, all elements of my right son, plus I will push back this 0, so I might have distance. So I will have all elements of my subtree. It's basically some non-recursive dynamic programming in some sense. See? So I go from bottom to top and push these values up to the root. Yeah? So every time I have element, I create it here. So here I create the element for the new node. And then when I iterate, I just push all values to the parent. So my parent contains all elements of my left son, of the left son, of right son, and itself. Okay, again, it's very short. That's like why I write it like this, but maybe not very clear. You may find your own way how to do it. You may calculate all the distances recursively and then push back. Up to you. It's many ways to do it. Okay, here I actually remember that I actually need to calculate two values. You need to calculate number of elements and also need to calculate this sum of distances. Yeah. And to calculate this sum of distances, I will calculate prefix sums. No, because I need always some prefix of this array. And for this prefix, I need to calculate sum of all the distances. You can easily do it using prefix sums. Let me see. So that's how I implement prefix sums. Yeah, just make array of size 1 more than you need, and then just push like this. So I usually make array of size 1 more. So first element is always 0, and then each element is the size of the prefix of this length of elements. So prefix of size I is all elements from 0 to I minus 1. Okay, here in some programming. Yeah, so I'm taking this. I'm taking this node A. So node A is my starting node. Look at the. I use this lower bound for the binary search. Yeah? So I use binary search to find the first element which is greater or equal than x. So all elements to the left will be less than x. You see, less than h. Yeah. So I have x elements less than h. I increased, so this counter is this number this, which will be multiplied by h in the end. I just thought I can I can multiply by h right here and calculate only sum. Okay, you can I care only of some of these elements. I don't need to keep them both. Okay, that's how I did it. Yes, so I increase counter by number x, and I increase sum of these elements by the prefix sum. Yeah, and now I will go up and do the same for the for these subtrees. So I go to one of my answers. So A is my answer. I need to go to the browser. Okay. Here I think too much about how to calculate the sibling of my element. Usually I do it like this, but here I'm again, if you go from 0, you can do it like this. Because 1 and 2 are siblings, and I think here inside I think too much. I believe you can do it using some bit magic, but at some point I decided I think too much about how to do it. How to do it how do you use bit magic? So I just did it like this. That's the way how you do it. Why not? Why not? So if number is odd, I make the I am the left sum. If it's even, I'm the right sum. So this is how you calculate the brother of your element. Now in this brother subtree, you need to yes. So you're looking for element h minus c. C is the length of this path. Minus c and minus length of this h. Yeah. Okay, here I spend too much time thinking why I'm incorrect. So it should be 11, but I see 12. Okay, and now I will, I will spend too much time. Okay, I write all this thing. I could just read the code first. Okay. But I decided it would be easier to debug if I actually understand what's going on in the problem set, because I didn't draw the examples, so I'm actually not sure if I understand statement correctly. Sometimes you just debug the program which is correct, you just misunderstand the problem statement. Also works. Yeah. So in here I counted, it should be 11. Yeah. So I understand the problem statement correctly. I just have bugs in my program. So let's see which bugs are there. Can you spot the bugs right here actually? Yeah. To debug this, I output both these values to check which one is incorrect. It turns out they're both incorrect, but you see. So here, so I see so I counted 4 nodes, and sum of distances is 4. It's nonsense. It shouldn't be like this. Yeah. So I have 5 nodes reachable. See. All these nodes are reachable. So it should be 5, and total distance is definitely not 4. Yeah. So I just now I just looking at looking at my program 5, trying to find the mistakes. There are multiple mistakes actually. So let's see. First of all, okay. Yeah. So here the total distance will be different. So this prefix sum contains distances from the root. So it will contain distances from this node B, from this pair. By the time looking at distances from my starting node A. Okay, it's called X here. We'll see. Show you once again. So A is my starting node. Yeah. Then I go up to some of the answers, and then here, this is node B. Yeah. So this prefix sum contains distances from node B, but I care about distance from node A, from the starting node. So I need to add the length of this path, yeah, multiplied by number of elements. So this length of this path is C, this path is L of B. Yeah. So I need to add C plus L of B multiplied by the number of elements, X number of elements. Okay, so that's the first mistake. Here also, the second mistake, why I have the first number incorrect, because I forgot about the answers themselves. So I'll calculate it. I counted all nodes in this subtree, all nodes in these subtrees, yeah, but I didn't count these nodes. Okay. So that's what I'm doing here. Okay, made a few mistakes here. Not that many as I could, but here I run timer and don't understand what's going on. What's going on is some elements do not have siblings. Yeah. So sometimes I try to pick sibling here, but it doesn't exist. Okay. And I spend too much time finding this problem. So again, I see I have bad access. It means basically I get out of the array. And I think how can I get out of the array? I have all arrays have this the okay. I have the good size. Why I have out of the array? Because I try to pick element which doesn't exist. Yeah. Oh, no, that's it. That's problem G. You can kind of long code. You have like almost 80 lines of code. That's more than we usually do in these contests, but overall, not that hard problem. Yeah. So you need to take some basically dynamic programming over tree. Then store some sorted arrays and by an search. Many steps. And again, the key idea is the initial tree is balanced. So the height of this tree is pretty small. That's why you can do all these things. If you have not tree like this, but normal tree, you need much harder algorithms actually. You can do it for regular trees as well using some centroid decompositions, I believe. But if your tree is balanced, you can track all your ancestors, for example, or you can store all your elements in your subtree. That's something you may be not very familiar to, but it is true. Only works when you have balanced trees. Good. Now we have another tree problem, problem H. In problem H, again, we have a tree, and we need to calculate something strange. We need to calculate some k area heap, whatever it means. Basically, what we need to calculate is we need to find some trees, some full k-nary trees, let's say so. So we're looking for trees of this form. So we have three. So we have some k. Okay, if k equals 3, we're looking at trees like this. So in every level, at every level we must have at least 3 elements. So we have 3 here. And maybe another, so and so on. Yeah. So if I have 3 like this, and also here, yeah. Then I have a k-area heap of this height. So and this is the height of the tree. And the question is basically find the maximal height of the tree you can find in your given tree. So given some tree, for every node of this tree, you need to find the maximal height of this balanced k-area tree, yeah, which starts in your position. Yeah. And what you need to calculate is this sum. Now it's interesting observation. So let's look at this sum. So what I need to do, I need to look at every node. So you take every node, you take all values k from 1 to n. Yeah. And you look at the maximal height of this tree you can have. Let's say h. So it's maximal height you can reach when you have k-area tree of this for this k. And you calculate some of these values. Why you can do it like this? Why can't we do it just like this? Why can't we calculate, let's say, just dp of u and k? It's actually kind of easy to calculate. You can calculate these values. The problem is there are too many values. Yeah, there are up to n square values. So u is the node, so there are n values here, n values here, so like n square values in total. Yeah, there is no way you can calculate n square values faster than n square, and n is kind of high. So n is very large in this problem, so you can't calculate it in n square. The trick we will use, okay, the trick is like this. Let's find something small. So you think that way. So you calculate sum of some values. Yeah, this value is height of some balanced tree. Height of the balanced tree is usually small. Yeah. So if k is greater than 1, so this value will be not greater than log n. Yeah. So you need to calculate sum of some numbers. Most of them are very small. And what we will do, we will group equal numbers together. So we will go in, we kind of invert the perspective. So we're trying to find the height for the number k. Let's invert it. Let's calculate k for the height, because there are less number of possible heights. You can think about it like this. Now, okay, so let's look at some nodes. You have some nodes. Yeah, there are some values. So this is k. So when you increase k, the height will only decrease. Yeah? Makes sense, right? So you have some value here, some value here, some value here, then some less value here, less value here. Okay. Something like this, yeah? And this is your height. You need to calculate sum of all these values. Yeah, for every k, you calculate maximal height and calculate sum of all these numbers. So this is the second. So this is sum for k. So sum for k from 1 to n. Let's say from 2. 1 is different. From 2 to n. dp k of u. So what I will do instead? I will group all these elements in groups by the same element. Yeah. Okay, another way to think about it is like this. Imagine you do it like this. So you need to calculate sum of all these elements is just number of cells in this picture, number of these small squares, right? You can calculate it column by column, but there are many columns. Or you can calculate row by row. And there are like log n rows. Yeah. So if I calculate number of squares for every row, yeah, I will calculate the same number. But the number of elements will be just log n. Yeah. To do this, I need to calculate following. I need for every height calculate maximal k, which gives me this height. Yeah. So I need to calculate maximal k. So there exists. So okay, you have function from k to h. Yeah. So this function is function from k to h. I will invert it. I will make function from h to k. It looks like n h. From h to k. So for every height, I will find the maximal like branching factor of this tree, which give me this height. And it's easy to calculate actually. Let me show. Okay, so I will draw a picture here, I believe. Shift a little. We're playing. Okay, here again. Here I'm just exploring the example. I checked that I understand the example. Actually, it looks like I'm not. Yeah. So here I spend a lot of time thinking why for you 1 and 3 you should output 2. It's actually not like this. You need to calculate, okay, for every, okay, I spent too much time finding why it's actually 2. It's actually kind of misleading. I'm not sure why they did it like this. Okay, spend too much time. Okay, I read problem statement multiple times. Okay. Finally here. So you need to count not the maximal height from your element, but maximal height in the subtree of your element. It actually doesn't change that much. You just need another dynamic programming on top of that, but it's a good step. So again, I draw the examples to check if I understand problem statement correctly. Yeah? Turns out I'm not. So it's better to find this problem before you start implementing something. Okay, so what I'm doing, I will calculate this dynamic programming for every node and every height. I will calculate maximal k, which gives me this height. How it calculated? If I fix the height for node v, I must look at the children. So I must have at least k children. So all of them for the height h minus 1 have k at least have at least mine. So I look at my children, look at the maximal k for h minus 1, and I need to have at least k values, at least k. Okay, next let me stop here. Okay, so I'll explain it once again. So what I'm trying to do, so I have the node, yeah. I want to find a tree with branching k and the height h. Yeah. To do this, I need to have at least k children. So for each of them, if I look at the tree with height h minus 1, yeah, this branching factor will be at least k. Yeah. Well, how to do it? You just do it like this. You take all your children, look at this value for h minus 1, sort them in decreasing order. Yeah, and look at the k maximal elements. So if k maximal elements are all greater or equal than k, then you have k elements all greater or equal than k. Now, out of all these values, you pick the maximal one. Okay. Okay, it will be a lot of coding, so let's watch. So it will be multiple DFSs actually. Yes, another thing, you also need to separately track the case when k equals to 1. So when k equals to 1, then dp is just the height of the tree. So you need to pre-calculate the height of the tree and to calculate the answer for k equals 1. Yeah. Okay, I will do it really strangely. So okay, so okay, I know I need multiple DFSs, so so I just copy this DFS. Again, calculate the height. Height of the tree is calculated like this. It's either 1 if you have a leaf, or it's maximal of the heights of your children minus 1. So that's how you calculate heights of all elements. Okay. So I calculate the height and just return it. That's it. And add it to the result. So again, result for k equals 0 is just the height of the tree. So this DFS calculates heights of all subtrees and just add this to the result. So now I don't care about case k equals 1. No, here I just check that my result is correct. So I correctly calculate the first part at least. Okay, now the second part. Okay, I need to calculate values up to log n. You can do it like this. You can find the maximal k you can have and then make array of this size. I usually do it like this. I just create a constant, which is kind of log n at least. Yeah. So I put 20. 20 is enough. So its number is less than million. If it's million, I put 21. So 20 should be enough. So I cannot have balance tree of height more than 20. Yes, and here I will what yeah, and this is my array dynamic problem. So this is my mine array for every node and every height. it will calculate the maximal k, which gives me this height. I just call DFS. Thinking. So the way I will do it is just like this. I will just make array of my children, then iterator all heights. Okay, yeah, I'm thinking about the starting value then. dx0 will be equal to, again, for the height 0, yes, I can have any k. So for any k, I can give height 0. So dx0 will be equal to n. Now I will put all my children to this array C. Now I will iterate all possible heights. Height should be, okay, it's not from 1 here. I'll do from 1. Okay. 1 is not interesting. No. Okay. No. Okay. Because I shifted everything. So 0 is 1 actually, because height is calculated in this problem, calculated in number of nodes, and I calculated number of edges, so it's shifted by 1. Okay, so I go from 1 to m. Yes, look at my children. This should be h minus 1. I will fix it later. So I take all my children, take their maximal case, sort them in decreasing order, because R begins in decreasing order, and then I need to find k elements greater or equal to k. So I will look at all values. Thinking too much. Yeah. So I check if I maximal values are all greater or equal than I. You only need to check the last value because I decrease in order. So only let's check the last one. So if first I values are all greater or equal to I, then I can build tree of branching factor equal to I. Yes. So that's it. That's basically it. That's basically it. No, it has some problems, but we'll fix it later. Okay. Here I just print the results just to check that everything works as intended. Again, it's a good thing I do sometimes when program is too complicated, contains many steps. I do some intermediate stops just to check that everything by now is calculated correctly. Yeah. So here you think you see that my array is already incorrect. So this is not what you should what you should be looking at here. So for example, so some of the nodes should have height 2, and I have only height 1. Height 1 is not very interesting. Height 2 is all zeros. It's not what, again. So what does it mean? It means I already have some problems. I already made some mistakes. It's much easier to fix them now than later. Yeah. So I will stop here and fix all the mistakes and then move to the next step. Okay. And I found this h minus 1. Yes. So this must be h minus 1. I check. Okay. Now we're talking. Yes. So here we have 2. So for the node 3, I have 3 of size 2, and with branching factor 2. That's correct. Check the second one is boring. It's just a bamboo tree. I check. Okay, I specifically built some tree with branching factor 3. So I check that I can have value 3 here. That's it. So by now it looks okay. So let's move to the next part. For the next part, again, you need to calculate not the maximal height in your element, but you need to calculate maximal element in your subtree. Yeah. So what I'll be doing, I'll just basically combine all these values using standard dynamic programming. So I will do standard dynamic programming to calculate maximal element in the subtree. Yeah. So for every height, I calculate maximal element in the subtree. It will give me the desired number. No, it's just boom, boom. Okay. Boom, boom, boom. So this is how you do it. Yeah. So you just look at your children and update your maximum. So when you go back from the recursion, you update your maximum. So in the end, you have maximal value in your subtree for all values of each. But it looks like it doesn't work because I'm stupid. Let me show. Okay, I spent too much time. It turns out, okay, let me show you the problem. The problem is I was writing this number before I calculate second dynamic programming. Happens. So now I fixed it and now it's correct. Yep. So that's it. So again, three DFSs. First DFS, just for the case k equals 1. Second DFS, calculate the main dynamic programming. And third DFS, calculate the maximum for each subtree of the first dynamic programming. Maybe you can do it in the same time. Probably yes. But for me, it's easier to split all the operations in several steps. Yeah. So it's easier to check that all of them work fine. So it looks like everything works fine. Now you just need to calculate the final answer. Okay, I spent too much time here. Okay, I'm trying to guess the correct formula. Spend too much time. Let's skip this. Let's keep this. Okay. Okay, come on. That should be it. That should be it. Yeah. So that's it. So so how do you calculate number of elements? So I look at every height. So I is my element, j is my height. Okay, you need to remove this break also. I will do it. Let's remove this break. It's this. So you look at every height and see how many elements give you this height. So you need to calculate sum of heights for every k. Yeah? And I have the maximal height for the given height. Yeah? So I take this height, here is j plus 1, because it's shifted. Remember, it's from 0, it should be from 1. So j plus 1 is my actual height. I multiply it by number of different k's that give me the same height. Yeah? So if it is the last element, so next element is 0. So it's the maximal possible height I can get. I just multiply it by this value. It's the maximal minus 1 because start from 2. Yeah. Yeah. I again, this is maximal k I can have. And my k starts from 2. K equals 1, we solve separately. Yeah. So I measure k from 2 to the given value. That is this amount of this case. And if it is not the last, I take all my elements up to the next one, because next one will give me less height. So my height will be for all this element up to this one. Okay, so this is finally the correct formula. Again, I spent some time just tweaking the formula back and forth, trying to make all these numbers correct. It happens. So you can spend some time with paper just trying to find the correct formula. I usually try to first just guess the formula, just tweak it a little bit. When I get wrong answer, then I will try to actually draw something. But here it works. Oh, here it's embarrassing. I have wrong answer. I have runtime error test 1. So I probably have some undefined behavior here. Yeah. Can you find where I have undefined behavior? It was actually much easier to find if I look at this part of here, see? So these yellow things are warnings. So C line actually warns me that something is wrong here. Okay, here, you should hear this. So this function DFS, yes, have this yellow line. Yeah. So it means you have some warning. And if I pay attention to this part, I would spend less time trying to find. But usually when you have something like this, you have some undefined behavior. Yes. So the first test works on my machine, but doesn't work on the server. It means I have some undefined behavior usually. Yeah? What you're looking for undefined behavior, usually it's when you go out of the bounds of the array. Usually, most probably. I don't have this problem usually because I put asserts in my vector calculation. So I checked I have assertions. Okay, so I just checked that I have assertions in my vector, that I don't have any problem with going out of bounds of the vector. Yeah, it's here. It turns out the problem is my function. I have, let me see. So here, unexpected actually. So this function do not return value. I copied it from this DFS. That's why you don't need to copy paste your code. Yes. So I make this first DFS and then copy paste it and keep this in here. It should be void. It should be void. It turns out it may give you runtime error. Yes, even if I don't use this value, you see. So you see this DFS, it must return value int. I never use this, but still it's undefined behavior. You don't do it like this. So you need to change it to void, both this. That's it. That was the whole mistake. Yeah, it's really embarrassing. Sometimes it may cause you a problem in the real contest. It would be really embarrassing. So that's it. So let me show you how to change this. I after the contest I found how to. So now let me see. So here, so you can actually change the settings of your IDE, at least for CLine, to mark it as error. So now you see, now it's red. Yeah, it will not allow me to compile this file. Yeah, it will. Boring. But okay, again, at least it marked it as a red, so it's more visible. So you go to inspections, the inspection profile, and here you have all the inspections you have in the CLine. There are many of them actually. Maybe I should mark all of them as errors. So this one was marked as warnings, and normally I have too many warnings in my programs because again it's not very nice C++ code. So normally I have too many warnings, so I don't pay much attention to this. But this warning is actually very serious. So if you do not return a value from your function, C++ does strange things. So that's how you actually what you should do is just to change this parameter to error. So every time you have problem like this, CLine at least shows you that you have serious problem here. Okay, so that's it. That's the whole code of the last problem. Okay, let's look at it once again. Okay, the first DFS just calculates the height. It specifically to solve case when k equals to 1. The second DFS, okay, let's remove this. Can you just do it? Poop. Poop. Yes, nice. Thank you, CLine. Second DFS calculates the main dynamic programming. So for every node and every height, calculate the maximal k. Yeah. So here is calculate value for height 0. It's easy, and here calculate for all other heights. Yeah. For all heights, I look at my children, look at them at height h-1, and check if I have I children, all of them greater or equal to I. If I do, I can make tree of size I. Third DFS is simple DFS, which calculates maximum and subtree, because the problem statement required to do it. Not sure why they decided to put this problem statement like this, but that's the problem we need to solve, and that's what we implemented. And here is just first DFS, second DFS, third DFS, and here we calculate the result. That's it. Again, the core idea of this problem is just that the height of the balanced tree cannot be much more than log n. So all your trees have small height, and when we move from function for calculating height for the value k to calculate maximal k for value h. Yeah? Again, let me show you again. No. How can I move to the previous? Here. Yeah. So that's quite popular trick. Moving from so you have some function from something to something, and your results are small. So your parameter is large, your results are small. You can inverse your function sometimes. It's not always work, but in many cases it does. So you just swap the result of your function and the parameter of your function, so you have less values to calculate. You can do, for example, the same thing for the knapsack problem. So sometimes in knapsack you have small weights but large costs. or you may have small costs but large weights. And you can, again, you can swap these parameters to calculate whatever is smaller. That's it. So that's all for today. Thank you for being with me. See you next week.